Math and Beats. In this video, what we're going to do is, as you can see by the title, we're going to come up with the general formula for the derivative of a logarithmic function. Let's do it. All right, like I said, here's the goal. We're going to find the derivative of a logarithm of base b of x with respect to x. And remember, whenever we're dealing with logarithms, the base has got to be positive and not equal to 1. So let's just let y be equal to this function, logarithm of base b of x. Then, of course, remember that if the y is equal to the logarithm of base b of x, that is equivalent to saying that b to the y is equal to x, because, of course, logarithms and exponential functions are inverse functions of each other. So I'm just going to rewrite that statement above, and we're going to use this in exponential form, b to the y is equal to x, to help us come up with the derivative of our logarithmic function here. So b to the y is x. What are we going to do? We're going to implicitly differentiate both sides of that equation, like you see right down there. I'm going to take the derivative of b to the y with respect to x, and that's going to be equal to the derivative of x with respect to x, differentiating both sides. Well, remember, y is a function of x, so by implicit differentiation, when I differentiate b to the y with respect to x, then I'm going to get this right here, right? The derivative of the y with respect to x, that's like our inner function, and the base to the y power, we got to differentiate that as well, giving us the natural log of b times b to the y times dy dx is equal to 1, because, of course, the derivative of x with respect to x is just 1. And now, if we just divide both sides by the natural log of b times b to the y, we get that dy dx is equal to this here, 1 divided by the natural log of b times b to the y. But we know what y is, so we're going to plug that back in to make our derivative strictly in terms of x. And that is, we know that y is equal to the logarithm of base b of x. And thus, by inverse properties, b to the y is equal to b to the logarithm of base b of x, which of course is x. And keeping in mind, this is true for values of x that are positive here. And so I'm going to replace that in my formula that we just came up with, which was this formula right here. And if I replace my y in terms of x right there, logarithm of base b of x, then b to that power is just x. And guess what we get? 1 divided by the natural log of b times x. And that is our derivative. Thus, add it to the list. The derivative of log base b of x with respect to x is 1 divided by natural log of b times x, all in the denominator. Now, note the special case. If the base is e here, then when I differentiate my logarithm, I'm really differentiating the natural logarithm here. And so, if I go ahead and use this formula, it's going to tell us that the derivative of the natural logarithmic function is 1 divided by the natural log of e times x, since e is the base, but of course the natural log of e is 1. So it's that special case in which you consider the derivative of the natural logarithmic function, you get 1 over x, kind of similar to the case of the derivative of e to the x, that special case, right? So this is widely seen in our discussions moving forward. Let's just find a few derivatives here. All right, first one. Let's find the derivative of log base 7 of 8x with respect to x. So that is technically a chain rule situation, which the inner function is 8x. If I differentiate that with respect to x, I get 8. And then times the derivative of the outer function, which is going to be 1 over ln of the base here, which is 7, times the input, but the input here is the inner function 8x. Notice the 8's cancel away, and we still just get 1 divided by the natural log of 7 times x. So say, hey, that's kind of interesting. My inner function 8x, it doesn't actually play a role here. That's just literally the same thing as the derivative with respect to x of the function log base 7 of 8x. So kind of interesting to point out. You think, oh, is that always true? What if 8 was some number n that defined this function? Then those n's would always cancel just like the 8's do. And that's because, of course, properties of logarithms, this is the same thing as differentiating the function log base 7 of 8 plus log base 7 of x. And since this is just a constant, when we differentiate it, it goes to 0, and we're always going to be differentiating just a logarithm of base 7 of x here. So you can think about how that might be generalized. Speaking of general derivatives, let's look at one. Let's differentiate the general logarithmic function base b of a function f of k, where we assume f of k is differentiable, and of course it satisfies the conditions of being positive to the inputs of the logarithm. We'll differentiate all this with respect to x. It's kind of like generalizing a situation in which we differentiate a logarithm of base b with some inner function inside. So what's that going to be? Well, this is a chain rule, right? I have to differentiate my inner function f of k with respect to k. That gives me f prime of k, or df dk, times the derivative of the outer function, which is the logarithm of base b. So we're going to have 1 over natural log of base b here. And then the input is f of k. So we can write this, if you will, f prime of k over the natural log of b times f of k. So you want to replace k with x, whatever you want, call it what you want, but in general, if I have any logarithm of base b that defines this of a function, then it's always the derivative of the inner function divided by the function itself times the natural log of the base. So that's kind of nice. Now finally, here's one last example to consider. Notice the input variable is called q here. Let's differentiate with respect to q the function, the secant function of the natural log of q. Another chain rule. So I'm going to have to take the derivative with respect to q of the natural log of q here. That's that derivative of that inner function, times the derivative of the outer function, which is that secant function. So remember, the derivative of the secant function is the secant function, in this case of the inner function ln of q, times the tangent function of the inner function ln of q. Differentiate ln of q with respect to q. Remember what we just saw earlier in this video. That's that special case. It's just 1 over the input, 1 over q here. So I guess we'll write it as secant of ln q times the tangent of ln q, all divided by q, right? Just same thing as that secant tangent times 1 over q. And there you have it. Bam, got it. So that's it. That's it for this video. This video was supposed to just derive the derivative of the general logarithmic function, which we did, right? We used a few methods there, some relationships between logarithms and exponential functions, and then we applied implicit differentiation to get our outcome. And then we looked at a few examples. So, until next time, this is Math and Beats. Later.